population, we already said normal population 1 means that sample size is greater than or equal to 30. Population standard deviation is known, and the sample is from it's a simple random sample. So it's from a simple random sample. No bias, so it's a simple random sample. Okay, all right. So then when it is non-normal population, we will assume that the sample size is less than 30, population standard deviation is unknown. So when it's non-normal population, sample size is less than 30, and population standard deviation is unknown, which means you don't know the population standard deviation, unknown. And then it also means that sample may not be from a simple random sample. So you have to check all these three out. You have to check all these three out before you start conclude. Okay. And in distribution of means, I'm going to draw a picture. I want to draw a picture so you know what can it look like? So we have been talking about distribution. Suppose you, I like to use that example. So let me pull that example up. I want to pull that example up so you see, even though we came here last time, I just want to make sure we understand this. Okay, so before we start reading or drawing a graph. Okay, so we have here the means of 200 samples. So let's get that question. This is approximate the sampling distribution of the sample means by obtaining 200 sample means from simple random samples of size 5. Okay, so this is what the question is saying. Suppose you get a sample. Let's see where they got the sample. Make sure we know where. So the weights of pennies in 1982, the weights of pennies in 1982 are approximately normally distributed. So with the mean, so that is the mean of the weights of pennies in 1982. And the standard deviation was this. Okay, and then they said approximate the sampling distribution of sample means by obtaining 200 samples of pennies with a sample size of 5. So they decided to collect sample size of 200. Actually, well, big sample. This is the big sample. Obtaining 200 simple random samples of n equal to 5. So imagine getting 5 pennies from maybe North Carolina and weighing it and finding the average to be 2.46, getting 5 pennies from South Carolina. And by the time we go to almost all the states, there are 50 states. Okay, it's not up to 200. Then we start going into maybe to the malls. Okay, get 200 samples. And after we collect those 200 samples of pennies, we find out that the means of those 200 samples is here. These are the means. So now the question is, if you draw a density curve or a histogram of this 200 sample sizes of n equal to 5, the distribution will be approximately normal. And these are pennies. Remember, the distribution is made up of sample means. Distribution is made up of sample means. The distribution is made up of sample means all right, and look at the mean. The mean of all these distributions is going to be the same thing as the mean of the original data. So the mean is equal to 2.46. Because the central limit theorem says it does not matter if the original data is skewed. So the original data here might actually be skewed right, or even skewed left. But if I collect 200 samples from this skewed right distribution, we call this one A, B, C. If I collect 200 samples of the skewed right distribution and draw a density curve of it, I will get the same mean as the mean of the original data. Likewise, if the original data is bell-shaped, if I collect 200 samples, different samples, and draw a density curve of that, I will get the same mean. Also, if the data is skewed left, if I collect 200 samples and draw a density curve or histogram, the histogram will look bell-shaped. So that is one argument of a central limit theorem. So that's one argument. Another argument, so the mean of the original data, mu x, is equal to the mean of central limit theorem. Argument number 2, the standard deviation of the central limit theorem, which is standard deviation x bar, is equal to standard deviation over square root of sample size. So how do I calculate the standard error? By the way, the standard error is the standard deviation of central limit theorem. Central limit theorem is called sampling distribution. Central limit theorem is called sampling distribution. Central limit theorem is called sampling distribution. So the sampling distribution of the mean is equal to the standard deviation of the original data divided by square root of sample size. Number three, all of them will be from a simple random sample. Okay, so another argument is that the z-score of central limit theorem, I'm going to write it down here somewhere here, so that the z-score of central limit theorem, let me pull this up. All right, so let's write it here. So the z-score of central limit theorem, Zx bar, is equal to x bar minus mu over standard error. So this is the z-score of central limit theorem. And this ordinary z-score of normal distribution is equal to value minus mean over standard deviation. Value minus mean over standard deviation. Okay, so before you start solving, you want to make sure that you know all these properties of central limit theorem. Okay, and then we will be given a question. So let's look at a question. Let's look at a question. The mean of 200 sample means this is the original data. Original data has sample size of 20, and this is the mean. But the standard deviation is now this is as expected. There is less variability in the distribution of the sample mean with n equal to 20 than with n equal to 5. And how did they collect it? How did they actually collect it? The standard error, which is the standard deviation of, is equal to the standard deviation of the original data, which is 2.46, divided by square root of sample size. And square root of sample size. So let me divide that. And I'm going to see what this one is. I will also later on divide by 20. Well, this is sample size of the original one. Okay, so I'm going to get my calculator and divide. Get my calculator. So it's still the same normal distribution, except that the central limit theorem is using normal distribution, and the standard deviation will now change to standard error. That is the difference. The difference is that the standard deviation will change to standard error. So I'm going to calculate this. Put it in my calculator. So I have 2.46 divided by the square root. I'm going to divide also by 20. So this time I'm dividing by 5, square root of 5. Dividing by square root of 5. And then I have, okay, well, that's it. And then I'm going to bring it down, second enter, and divide by square root of 20. So the important thing is that the larger the sample size, the smaller the standard error. So I'm going to hit enter. Okay, and I'm going to divide by 200 also. So I am going to divide, second enter again. I will divide by 200. I'm trying to show that the larger the sample size, the smaller the standard error. See, the larger the sample size, the smaller the standard error. Okay. Anyway, so see the formula for standard error here. See the formula for standard error. Okay. Now let's okay, so if you are told to find the mu x bar, so you already given the mu x bar, and it depends on the size of the sample. See, when the sample size is 10, the standard error keeps getting smaller. Okay, and then the z-score. See the z-score, because you could be told to find the z-score of central limit theorem. When you're told to find the z-score of central limit theorem, we already put the formula in here. Okay, what is the probability that z is greater than 0.79? Okay, and 0.79 here is, you put it from your calculator, you calculated the z-score, and then you find set that to find the probability. And that probability is the area to the right, because it says greater than. It says greater than. So we're going to find in our calculator. By the way, you can actually do this, put them all in the calculator. Let me make sure you know you can put that in the calculator. So I can actually find the that area. So I can do normal CDF. So I'm looking for the area to the right of the number 2.465. Okay, so 2.465 is the, let's see which one is lower bound. So this is we're going to start from where the boundary is. 2.465 to positive infinity, 1e to power 99, comma, the mean is negative, actually the mean is 2.46, and the standard deviation is 0.006, 0.0063, 0.0063. And then we can get a calculator and calculate what. So let's calculate. So let's calculate. All right. So I'm going to do second distribution, and I'm doing normal CDF. Number 2, the lower bound is 2.465. The upper bound is 1e to power 99. That's infinity, positive infinity, 1e to power 99. And the mean of this data is 2.46. And the standard deviation of this data is 0.0063. 0.0063. So I'm going to calculate. Okay, so approximately, let's see. So we have approximately there. Okay, that's from my calculator. That's what we have. So it depends on what our numbers are. So, and then while we're looking for area to the right. Looking for area to the right. Okay, so we will go to, let me see, we have to go to, and it depends on the size. It depends on the size of the sample size. The size, as the size increases, the standard error decreases. As the sample size increases, the standard error decreases. Okay. All right, so we are going to go to the practice question now. Let's go to the practice question and get a question. So we have to be careful when to determine when the question is actually on ordinary normal distribution. Let's read this question. Number 24. Determine the area under the standard normal curve that lies to the left. So I'm told that this lies to the left of 1.57. This one lies to the left of 0.72. This one lies to the left. All these are to the left. So I just have to do one of them since they are all to the left. I'm just going to do one so that we could go and do another one. So I'm going to pull up my whiteboard. All right, so my whiteboard is taking time to open. My whiteboard is taking time to open. I might as well get my, let me see if I can do it on, let me do it in Microsoft Word. This, I hope this one acts better than my whiteboard. Yeah, so hopefully it acts better than my whiteboard. So this is Microsoft Word. Okay, and this In this question, we are asked to, so I'm going to pull this up. The first question says, find the area to the left. Area to the left is cumulative area, and I'm given Z, so I'm using normal CDF. If I'm given area to find Z, the other class we said we use inverse norm. That means if I'm given area inside the normal curve to find Z, then I am going to be using inverse norm. So I come over here and okay, so the Z given to me is positive, therefore it's on the right-hand side of the mean. So for A, I have Z equal to 1.57. So 1.457 is here, approximately 1.57. And I am told to find the area to the left. What is the area to the left? Okay, and this left means you can include -1 e to the power 99. I hope you know that this the normal curve extends to -infinity. Okay, and I'm looking for area from here, and this area is going to be greater than 0.5 because the mean divides the normal curve into two equal parts. The mean divides the normal curve into two equal parts. Okay, so I am going to do normal CDF. Okay, so I'm going to do normal CDF. But what am I putting in normal CDF? See, it is normal cumulative density function. The lower bound is -infinity, so -1 e to the power 99. The upper bound is 1.57. The mean normal distribution is 0. The standard deviation is 1. So I'm going to calculate the area to the left. I'm going to calculate the area to the left of this normal curve. So that is what I am told to do there. So I'm going to go to my calculator. Remember how to find normal CDF, second distribution or second verse. Number 2, and the lower bound is -infinity, so -1 e to the power 99. I want to make sure that you know how to type in e, -1 e to the power 99. And then the upper bound is the value of Z that we are given, and that is 1.57. 1.57. And the mean of a standard normal curve is 0. The standard deviation of a standard normal curve is 1. And I'm going to paste. Remember, I'm told to find the area. So area to the left. So the area to the left is 94.18%. To 4 decimal places is 0.9417. So that area is 0.9417. 0.9417. That is the area we are talking about. That area is 0.9417. Okay. All right. I'm going to do another one to make sure that everybody understands that this is the practice test. I'm putting questions from practice test. This practice test is already in Blackboard. It is already already assigned it. I have assigned it in my lab maths. It's in Blackboard. I am going to write you an announcement today before you go on spring break to make sure you study for Unit 3 test. Okay. All right, so the next thing is go back to that question. Okay, the next question is this. They are saying, find the area to the left. I want you to see the question. Find the area to the left of 0.71. Find the area to the left of 0.71. Okay, whenever you're told to find the area to the left, it actually means draw a normal curve, find the cumulative area. Okay, what is the percentile associated with 0.71? Okay, so and 0.71 is positive. This z value is positive, therefore it's on the right-hand side of the mean. So I kind of know now the kind of normal curve I would draw. So I'm going to draw the normal curve associated with this. See, for any question on normal curve, you have to draw a normal curve. So this question is another question on normal curve. Draw a normal curve. And read the question very well and make sure, be careful to know when the question is on central limit theorem. I mean, I'm talking about central limit theorem, in other words, distribution of means. But this one is not. Okay, so what do I know? I am already told that that I'm looking for area to the left of 0.71, z equal to 0.71. Z is equal to 0.71. So it is on the right-hand side of the mean, because remember that the mean is 0. When z is equal to 0, it is the mean. So I'm told to find the area to the left. So just draw it, take your time and draw it. And then the normal curve goes to negative infinity to the left. So negative 1e to the power 99. Okay, so we're about to calculate. We are about to calculate this area. I want to make sure I'm doing this well. I have done so many examples of this because for some reason students get confused with this question. That's why I'm making sure that I'm doing it a whole lot of time. I'm doing so many examples. All these examples will make sure you understand how to do it. You can't run away from this question because it continues from unit 3 to unit 4. So this is a continuation. After unit 3, it's going to be in unit 4. So you really want to know how to do this. Okay, so normal cumulative density function. What is the smaller number? Negative infinity. And remember that your calculator does not know about infinity. So whenever it's negative infinity, you put in negative 1e to the power 99. Okay. Now, what is the upper number? Z equal to 0.71. So 0.71. What is the mean of central limit theorem, or what is the mean of standard normal distribution? It's 0. What is the standard deviation of standard normal distribution? It is 1. Okay, now you can calculate. By the way, you can actually read this from the chart. So after this, we're going to read the chart. So you know you can read it from the chart. Okay, so I'm going to pull my calculator up and I will put this in my calculator. Second. Okay, second distribution. Number 2. And the mean starts from the negative infinity. So I already typed in negative infinity. I would like to type it in again, just in case you don't know how to type it in. So negative infinity is negative 1e to the power 99. And then z value of 0.71 is 0.71. The mean of a standard normal is 0. The standard deviation of a standard normal is 1. So I'm going to paste. And it's asking me, is this correct? Is that what you want? Yes. Because I'm told to find the area to the left. Area to the left of the normal, of this normal distribution. When I hit enter, it gives me that the area to the left is 0.7611 to 4 decimal places. I could be told to write it in percent. If I'm told to write it in percent and 2 decimal places, then it's going to be 76.11%. So 76.11%. So 76.11%. So if I'm told to write it in percent, I can write it in percent like that. I hope you're following. I hope you are following. Okay. All right. So we go back to the question and make sure we solve a lot of them. We really want to make sure we solve a lot of questions. That way, so I'm going to, let's go back to that question and make sure we are doing more of it. Okay, so we have done a lot of questions that says area to the left. By the way, let's read this from the chart. So I'm going to pull up the chart. So at this time, I'm going to pull up the chart. I can read the chart. You get the same answer. You can use the calculator. The calculator is more accurate though, but anyway, whichever one you like, you can use. You can use the chart, but the calculator is more accurate. It's good to know how to use both of them. In fact, it's important that you know how to do both of them. By the way, the calculator steps is not it's not going to be given to you, so you have to remember the calculator steps. If you think that you don't remember the calculator steps, then you must use the chart. Okay, so I'm looking for the chart now. There are so many charts. The first one is T distribution. I'm not looking for T distribution right now. We're going to look for it later on. Okay, and I am going to the Z standard normal curve. So I just want to make sure you remember that standard normal curve finds the area to the left, the cumulative area, the percentile. So this is the standard normal curve here. It finds the percentile, the cumulative area. So we call this the percentile. Area to the left of a normal curve, that is what we find all the time. In other words, whatever you're going to read here is, okay, so let's read 0.71. Let's read 0.71, what we just found. So what is the number? I think I'm going to make it bigger. I'm going to make it bigger so I can read 0.71. Okay. All right. So I'm going to read the area, which is 0.71. I just found that from calculator. I want to find it from chart also. So I am going to read 0.71. Remember that 0.71 is positive, so you cannot be looking at the negative side. Okay, here is 0.7 right here. Here's 0.7. All right, I see 0.7. That's 0.7 right there. Okay, what are you doing? Okay. So this is 0.7. And I have 0.7. It doesn't, okay. So I see 0.7. 0.7. And then 0.71. So note that this is 0.70, 0.71, 0.70, 0.71. So our answer is 0.7611. 0.7611. Either way, when you do it with calculator, you get the same answer. When you do it by hand, you get the same answer. So you get the same answer anywhere. If you read the chart correctly, you get the same answer. All right. Maybe we have to read another one from the chart. Okay, let's read another one from the chart. Instead of using calculator this time, we want to find the area to the left. Let's find the area to the left of, okay. What is the, okay, come on. Okay, yeah, so let's find the area to the left of negative 1.35. What is the area to the left of negative 1.35? Negative 1.35. So I am going to open the chart now, and I'm going to be reading negative 1.35. So I will scroll to where I have negative, then I'm keep scrolling until I see negative 1.3. Okay, so here is negative 1.3 here, negative 1.3. Okay, and then I will keep on going to the right, and negative 1.0, 0.1, 0.2, 0.3, 0.4, 0.5. So here's it. So negative 1.35 is right there. So I got negative 1.3 and then negative 1.35. Okay, so you can actually read the chart. If you don't want to use your calculator, or you forgot the formula for using the calculator, then read the chart. If you forget the formula for using the calculator, then read the chart. Okay. All right. Okay, so we're going to start review. We will start review on central limit theorem. Next class, we will start the review on central limit theorem.